Thanks, everyone. As Courtney mentioned, my name is Ben, and I'm the co-founder and CTO of Kaggle. And let's see, whoops, is this not working?
Okay, take two. Wow, that's a lot better. Well, thanks a lot, Courtney. I'm really excited to be here. And as Courtney mentioned, my name is Ben, and I'm the CTO of Kaggle. And I'm here to talk to you today about the future of Kaggle, where we came from, what we've learned, and where we're going. But before I do that, just to get a quick view of the familiarity with Kaggle. First, raise your hands if you're familiar with us. Now, keep your hands up if you have a Kaggle account. Keep your hands up if you've made a submission in one of our competitions. Keep your hands up if you've won or actually came into the top 10 in one of our competitions. Okay, so 2 people can give this talk for me instead. Awesome. And then finally, keep your hand up if you've made a data set or kernel in our platform. Cool, several. Let's go ahead and dive into it now. So our mission is to help the world learn from data, and we really see ourselves as operating at the intersection of people, data, and code, and building software that facilitates the combination of those 3. And we got started off, as it seems like almost all of you are familiar with, running supervised learning competitions where we democratize access to data and real-world challenging machine learning use cases. And we're now doing this at scale. We've run hundreds of general competitions and thousands of universally paid classroom competitions. And this has put us in a really fortunate position where we've attracted a really talented and diverse community from all around the world. And as well as it's helped us to teach and introduce hundreds of thousands of students and hobbyists about machine learning and really get them excited and passionate about the field, as well as enable us to help push and do our part to push the state of the art forward, from introducing some of the first use cases that deep learning was successful at outside computer vision and natural language processing or audio, like molecular activity prediction, as well as pushing the state forward in medical diagnostics. And then along the way, we've really learned a tremendous amount. We've learned what techniques work well in which problems. We've learned how people go about winning competitions. We've learned how our community participates in them, as well as major pain points that data scientists hit, as well as how we can help data scientists ameliorate these pain points. And just several of the lessons that we've learned is, first, really great data scientists optimize the entire end-to-end machine learning workflow, not just the kind of sexy component, the machine learning piece of it, but everything from sourcing data, splitting the data set, cleaning the data, etc. And a lot of the times our innovations or the really powerful improvements to models do not come from machine learning or the optimization pieces, but instead they come from earlier stages in the pipeline. How are they framing the problem? What data sets are they using? Can they find a more powerful data set to help with the problem? And things along those lines. But of course, everyone's favorite part seems to be the machine learning specific component of the workflow. And I don't think it's going to be a surprise to many of you that gradient boosted machines or variants of ensemble decision trees and deep neural networks are incredibly effective across most problem types, whereas deep neural networks work well at any form where there's a natural hierarchical structure to their problem, like images or speech or video data or molecular data, things along those lines. And ensemble decision trees tend to work well on almost everything else. And these 2 methodologies alone have been key components to winning almost every competition that we've hosted in the past 2 or 3 years. Another lesson and key takeaway is model ensembling almost always ekes out performance gains in a solution. It really results in a big leap forward, but almost always ekes out like an additional 1% to 5% or so performance gains. And each organization can weigh for themselves whether the trade-off in the engineering complexity is worth it for implementing that in production. Another lesson is successful participants are really careful about avoiding overfitting. This has also led to a lot of funny stories. For example, this user is coming in second in a competition going into the end of it, and then we split the leaderboards into a public set and a private set that's only revealed at the end, with the private set being the only one that actually matters. And then he was sitting there hitting refresh on his keyboard, as the competition was about to end, hoping he could move from second to first place. Finally, the competition ends, leaderboards flip over, and he starts looking down the leaderboard. He's not in first place, not in second place, and has to start hitting page down on the keyboard to actually get to where he was. It turns out he dropped 50 places in a minute in the competition, and he's never overfit again.
Then another thing that we've been really in a position to see is we've seen major pain points in how data scientists and how machine learning engineers tend to approach problems. This is true from what we've seen from how our customers' data science teams function. It's true from our own experiences. It's true from our experiences collaborating with our customers. It's true from what we've seen about our users and how they approach competitions, both individually when they're working by themselves, as well even more painfully when they're working in teams. And I see really today's machine learning and data science practices as kind of like the software engineering equivalent of programming in assembly. And then the tools that we have available to us right now feel like they came from the Stone Age compared to the software engineering tools that are available in the broader software engineering ecosystem. And just some of these that we've seen is, first, it is really tough to access good data. You have to cut through a lot of red tape to do that, and many times that data doesn't even exist yet, and you have to instrument the processes to go and collect what you need. Secondly, it is even tougher getting access to high-quality data. Most data that you get or that's sent to you ends up being a complete disaster in some capacity and is a big mess that you need to sort through. Thirdly, cleaning that data can be really painful. Just a couple examples of the thousands that we've experienced are, we've had a data set where planes landed before they took off. We had bulldozers manufactured in the year 1000 because someone thought that 1000 was a good number to use for missing value. We've had essays that got perfect scores that said things like, this essay got good marks, but as far as I can tell, it is gibberish because the transcriber didn't follow instructions that should have dropped that essay from the set. And the machine learning models all have to either account for these types of errors and be robust against them, or they need to be filtered out early in their process. I imagine anyone who's worked with data in a real-world scenario has hit many of these before. Who's hit many pain points like this before? Yeah, most of the room. Awesome. Another one that we've hit is data leakage is both really common and can be really subtle. Just one kind of simpler, more obvious example of it. This is a data set. Apologies, I don't know if this is actually coming through very visibly, but that we got about prostate cancer surgery, and then we're looking at, about prostate cancer and identifying whether or not a patient was likely to have prostate cancer. And then one feature in it turned out to be really predictive. It's that little one ambiguously named cross-search that's highlighted in red. And it turns out that one stood for whether or not the patient had prostate cancer surgery, which naturally was very predictive of whether or not the patient had prostate cancer, but it's completely useless in any sort of applied scenario. And then most forms of data leakage are far more subtle than that and can be far tougher to detect, and you just see that the model's not working as good as you thought. You don't see the obvious root cause immediately. Another thing is going from research to production can be really brutal. Many times it takes twice as long, 3 times as long as you thought it would because there's so many engineering difficulties in place to go from research to production. And then once you actually get there, many times you see your performance drops instead of increases because you missed a key assumption about how the data worked or if something changed with the distribution of the data. And then finally, one thing that really kills me is just how tough it is to reproduce work that others have done, whether it's work that you did 6 months ago and you're trying to do again now, whether it's work that your colleague sitting next to you is doing, and you want to take that work and do it on your own computer. You might hit something like a Python version conflict or a Python library conflict. Or if it's a work that your coworker who's at an upstream stage in the workflow from you on the data cleaning step did, and then you want to tweak one aspect of it that was wrong, but it ends up being a weeks-long project because you don't have everything that he'd done that fed into that, or it's reproducing that good academic paper that you want to take and incorporate in your own work. I think it really pains me just how much time is wasted spent reproducing work that other do. I think there's one and only one good reason you should be reproducing work, and that's because it's an effective way to learn about it. But things like working through Python library conflicts are a complete waste of time. So my viewpoint is we can do a lot better than this right now, and we can make things a lot better for machine learning engineers and data scientists and anyone who's working with data. And aiming at a couple different principles. First, accessing data should be as seamless as possible. Secondly, you should never need to repeat work that others have done. And we should make it really, really easy to not need to repeat work that others have done. Thirdly, a single command should reproduce everything start to end, and no matter how simple or how complex your data workflow might be, or what underlying technology you're using to represent that pipeline, it should be all wrap up into a single command that says rewrite everything from start to finish. And for those of you who haven't used it for data workflows before, is a perfectly adequate tool for a lot of different data workflows. There's many others out there. I don't think there's a great one that exists yet. Another principle is making a successful one-line update should take seconds, where there's just one line that you want to change. You should be able to go in, change that, then have that propagate through the entire system. Now, it may take a lot longer for it to propagate through the entire system, but you shouldn't have to do anything else for that to happen beyond making the change. If it turns out that change broke something or led to unexpected consequences, you should get a notification that that happened, as well as a pointer for this is a step that broke, and here's the inputs right before that step, so you can diagnose and debug that change really quickly. Another one is helpful metadata shouldn't stay buried in mines or people's emails. You shouldn't have to go through a forum thread that's hundreds of items long or sort through a massive email chain to understand what a specific column in a data set means or why a field is the way it is. That should be surfaced to you right when you're working with the data. And finally, best practices should be easy defaults and not complicated custom contraptions. And what we see right now is every data science team or every engineering team tends to invent their own set of best practices that their team uses, and many of them are actually building out the same technologies, but it takes a lot of time and a lot of effort to build these and put them in place. So we're working really hard right now to try changing this and push the ball forward. And I'm going to take a moment to try launching into a demo for the kind of very first foray that we've taken in this direction, which represents early prototypes. And let's see if this is going to work. I'm currently tethered to my phone, so I have no idea if this will actually work or not. So for this demo, I'm going to first drop into a competition that we recently launched with Quora on identifying question, or whether two pairs of questions have the same intent, which is one of the many, many machine learning problems that they face in running their product. And for those of you who haven't used the product before, it's both a really fun product and also has machine learning effectively touching every single aspect of it. And let's see, good, this connection actually worked. So what the first thing that we've built does is it enables you to drop right into a data set and spin up a Jupyter Notebook session or a coding file on a data set immediately. So I can click here and see what the data set is. It's a data set that has different question pairs in it. I can drop in. Let's see if this is going to work. I'm going to make my own little microphone holder for a second. How many of you have used Jupyter Notebooks before? Probably most people. Awesome, yeah, Jupyter Notebooks are an awesome product. I'll go ahead and read the training set in. So one of our principles that we're trying to keep is it should be really easy to access any data set and get into the libraries that you're familiar with as quickly as possible. As we see here, then I can just do a quick operation to see something like how many duplicate questions are in here. I see that there's an is duplicate column in the data set that I'll use. And for those of you who don't currently use Jupyter Notebooks within your organization, I think they're a really fun way to kind of quickly both access data as well as share that back with your colleagues. And one thing that we've been really focusing on doing at Kaggle is enabling a good environment for encouraging collaboration on problems. So the current defaults that we actually have in kernels while the product is early is everything done in it gets published here. So this was just a quick, easy example. But I can actually go through and see this competition launched about a week ago. all the different code that people have written and shared so far on that, and this creates a really rich library of code that's helpful to get started on a problem and inspire your own work. For this specific problem, I can see things like, as you'd expect, questions that tend to share words have a similar intent, or are more likely to have a similar intent to be duplicate questions than not, and that it gets even improved more if I apply IDF to the problem. And this prevents me from needing to do a lot of the same work that others have done, as well as provides a good launching point for starting my own work. If I wanted to start my own work, I could click Fork Notebook, and I immediately drop into the same computational environment and the same data set that was originally used to do this. So I'm making this as reproducible as possible. That was the first piece that we did. Then we actually, once we saw we made it easy to share code and on the same data set, that actually increased collaboration by over 100 times in the competitions that we host. Whereas previously we might see 5 or 6 code examples shared in the forums of a competition, now we see 500 to 600. So just a small change like that, making it easy to share code examples in a reproducible way, dramatically increases the collaboration that we observe. And we believe the same will hold true in all the organization by making it easy to share and collaborate code in your internal data science teams. And in a very similar vein, we've started enabling this in non-competition data sets right now and are building an open data platform, Kaggle Datasets, where we're trying to both collect the underlying data, have a nice interface to access that that's far more than a CSV file, as well as collect the code that's written on top of the data, provide that in a reproducible way, and then finally collect metadata that's written on top of the data and crowdsource the collection of that so any user can drop in and improve data dictionaries. And if they find something that they're confused by, ask a question about it, and if they find the answer, mark the answer here. So I can say things here like poorly described fields in this traffic data set, like per not MVIT. I have no idea what that would mean. I can see it's the number of people that were not involved in the, not in the motor vehicles, but were involved in a collision. And with that, I'm going to try dropping back into this presentation. Perfect. So we see all the work that we've done so far as less than 1% of what we'll be able to ultimately achieve, and we think we can have a much broader impact in the world. Then to that front, we recently joined Google Cloud to both accelerate our growth, as well as Google made a really compelling case that if we took the world's largest machine learning community and combined it with the best organization in the world, or the organization with the most machine learning researchers plus a compelling cloud platform, we'd really be able to take this to the next level. So on that front, both datasets, kernels, and competitions all have an exciting future. Our goal is to have the world's data accessible with a common interface and to have all the data that you need to use, publicly or privately, accessible through a common interface instead of software primitives. That both makes it really easy to capture the code and metadata on top of it, as well as share and collaborate with others, and provide a central searchable hub for your organization's data. On the kernel side, we see a kernel as an atom of reproducible data science that's built on top of core open source technologies that combines version code, version data, and a version computational environment to produce a reproducible result. And then that could be flat files for data, it could be streaming data that's coming in and changing over time. And the important piece of this is that every time something in there changes, whether it's a versioned computational environment through a Docker container or a piece of code or data, the results gets rerun, and ultimately you're given a CI server for data that when a data distribution changes and it breaks something, you get an alert that it changes. So you're kept up to date by default instead of being stuck on something like Python 2.7 by default, and you only need to change things when the updates break things. We've also started running code competitions. We ran the first one on a financial modeling backtesting problem with our partners 2 Sigma down the street. That just wrapped up, and we see this as enabling ultimately a very exciting set of new competition formats, from backtesting time series to live data feeds and reinforcement learning to generative modeling and adversarial learning, machine learning under computational constraints in sensitive datasets. So we're really excited to expand beyond the realm of supervised, purely supervised machine learning competitions and help really bring the rest of these problems to the world in an accessible way. So thanks a lot for taking the time to listen to me, and thanks even more for participating in on Kaggle and in our community. We just can build the software, and the thing that makes Kaggle really valuable to our users and to the world is all the actions that you take as part of it, the data that you share, the code that you write, and the competitions that you participate. And so thank you so much for that.